Hi, my name is Rohan Prabhuram, and this is my video lab report for Physics 2212, amount of excess charge on an ordinary object, or the charge tape lab. In this experiment, I prepared two strips of clear tape using the triboelectric effect. I observed how they charged, or how they interact when charged, measured the distance at which one tape floats above the other, hand calculated the net charge, and built two computational models in Python, a point charge model and a line charge model. The work relies on two fundamental laws. So first, Newton's second law gives the weight force as mass times gravitational acceleration. And second, Coulomb's law states that the electrostatic force between two charges is the Coulomb constant times the product of the charges divided by the square of their separation. The Coulomb constant is 9 times 10 to the 9 Newton meter squared per Coulomb squared. And at equilibrium, the electrostatic weight force equals the weight. To set up this experiment, I cut two strips of tape 20 centimeters long and folded each end to make a non-sticky handle. I stuck one strip flat as the base tape, peeled the other strip off by its handle, and charged both by brushing my hand near the sticky set. I confirmed they repel, then slowly lifted the hanging strip until it floated at a 1 centimeter separation. These are my quantities. So from the tape length of 20 centimeters and specification of 1 gram per meter, the mass is 2/10 of a gram, or 2 times 10 to the minus 4 kilograms. The weight force Fg is then given by these calculations and is 1.962 times 10 to the negative 3 newtons. And then setting the electrostatic force equal to this weight and solving for Q gives a value of 4.67 times 10 to the negative 9 coulombs, as you can see from these calculations. And then dividing by the elementary charge yields roughly 2.92 times 10 to the 10 excess electrons. In the point charge model, each tape's charge is concentrated at its center, and the field at the floating tape is given by E, which we calculate to be 4.2 times 10 to the fifth newtons per coulomb. And the force Fe is 1.9628 times 10 to the negative 3, which matches the value given by the Python model. This is my code. In the line charge model, I split the total charge into 10 equal segments along the tape's length, and summing the pairwise Coulomb forces gives a force of 2.255 times 10 to the negative 4 newtons, when Q equals 4.67 nanocoulombs. I rescale Q so that this force equals the weight, and it gives me a value of 1.38 times 10 to the negative 8 coulombs. This is my code. So the point charge model yields 4.7 nanocoulombs, where the line charge model yields 13.8 nanocoulombs, a factor of about 3 difference. The point model underestimates the field of an extended object, whereas the line model accounts for the distributed charge, making it more realistic for the type of tape that I was using. And to estimate the fraction of atoms that donate an electron, I assume a tape width of 19 millimeters, giving a sticky surface area of 3.8 times 10 to the negative 3 meters squared, with an atomic footprint of 10 to the negative 20 m squared. Meter squared. The surface contains about 3.8 times 10 to the 17th atoms, and dividing the excess electron count 2.92 times 10 to the 10 by this atom count gives a fraction of 7.7 times 10 to the negative 8, or 0.000000077%. If the electrons were positive and protons negative, two tapes with like charges would still repel and flow. Only if one tape carried net positive charge and the other net negative charge would they attract and stick together. So some of the assumptions and limitations behind this model are that these models assume static equilibrium, vacuum permittivity, and idealized charge distributions. The point model treats all charge at a single point, and the line model treats the tape at 10 point charges along its length. Both ignore tape width, thickness, fringe fields, any oscillations, or even air humidity, which all have a role to play. So in conclusion, a single strip of clear tape holds on the order of a few nanocoulombs of net charge, about 4.7 nanocoulombs in the point charge model and 13.8 nanocoulombs in the line charge